Hello, everyone. Welcome to the third CU Prime Talk of the fall 2020 semester. Thanks for coming. For those of you who are not familiar with CU Prime Talks, Graham, would you mind going to the CU Prime Talk slide? Thanks. The CU Prime Talk series is a bi-weekly talk series that aims to accomplish these things, mostly trying to foster an inclusive community in the physics department through these jargon-free talks that we put on. Yeah, so we hope that the CU Prime Talk series serves the purpose of kind of humanizing the scientist in all of your minds and giving you people to talk to about science and learn about science with in the CU physics community. As per usual, if you have a camera, please turn it on because it's easier for our speaker to talk to a bunch of people's faces rather like floating heads. If not, that's okay. Again, there'll be discussion questions along the way. So use that time to turn your microphones on and say hello and talk to people, socialize. Yeah, so our speaker today is Graham. Hi, Graham. Thank you so much for agreeing to give a CU Prime talk. I've been friends with Graham since we started graduate school at the same time together. Graham and I play music together sometimes. And I've somehow made it this long knowing Graham and never learned about his work. So I am very excited to learn about what it is Graham does today. No, I'm kidding. Graham, thanks for giving your talk. You can start.
Okay, thanks for having me. Yeah, there's sort of an unwritten rule among some grad students that you try to not talk about your work as much as possible. But here I am. So thanks for having me and welcome to the talk. And before we get started, I wanted to go back to that title slide and talk a little about it. Quantum mechanics and atomic engineers. I like to tell people I'm a quantum mechanic. And I like this title because mechanics don't get a lot of credit for the knowledge that they have, even though it's often extremely technical and thorough. And people say anyone can become a mechanic. Well, as a quantum mechanic, people assume just the opposite. And I'm going to tell you today that that's wrong. Just like a car mechanic, my main job is to be able to troubleshoot problems. And like a car mechanic, that sometimes leaves me with a little bit of specialized knowledge that the rest of the world doesn't really care about. But there was a time that the ideas of quantum mechanics were too magical, the math too arcane, and it was really inaccessible as a field, but that time is long past. So I like to start out with an outline of the rest of the talk. We're going to begin with a little bit of introductory background information about me, and then have a quick breakout room just to give introductions to each other. And then I'm going to jump back to physics. And I want to spend most of the talk talking about this basics superposition and entanglement section. That's what I really want you to understand today. And if you follow along, you'll understand a little bit about the work I do, but I'm really going to lie to you about it and skip over as many details as I can. And then we'll bring it back with a day in the life of a grad student and have an open period for questions. Okay, so a little bit about myself. Well, back before the pandemic, I would get invited to a lot of parties. Maybe not the type of parties that really spread the pandemic, but I'm a pretty popular person. And I noticed a recurring theme in conversations. With some people, these conversations would last for hours. We talk about science and what I study. And with other people, the conversation would immediately peter out. And these conversations, especially with people above a certain age, they would often go like this. Okay, acquaintance says, what do I do for a living? And I say, well, I study physics. They say, oh, what kind? And when I say atomic physics experiments, which is the right answer, almost invariably I would get these responses, oh, brainiac, or, oh, you must be so smart. And I really don't have anything to say to that. And I could tell that, that's not a conversation that they really wanted to have anymore. Oh, and also a lot of people tell me about their niece and nephews who work in the chemistry department. I also don't know anything about chemistry, so I don't know what to say to that either. I thought I took that out of the slide. Well, I changed my approach, okay? And so I started giving a longer answer. When they say, "What kind of physics do I study?" I'd say, "I study how atoms interact with lasers. Well, we cool down the atoms to engineer a really simple system, and then we watch what happens." It's mostly fundamental quantum mechanics type stuff. Now, if that doesn't get them interested, well, first let me say I think the longer answer gives people time to think of a follow-up question. How cold are these atoms? How do you cool them? Why do you use lasers? What usually happens? But if I can't get them going with a real response, well, I can either consider the conversation a loss and commence extraction, or I try something else. And my usual approach for trying something else is one of these two responses. Well, it's a lot like playing with Legos. And it really is. They give us these kind of toys that we buy from companies. We set them up in a certain way that the company expects us to set it up, and um, but really, we're building our own experiment, our own big Lego set, just to see what happens. And sometimes they say it's a lot like like learning a foreign language. Sorry, it takes time, and good teachers help. And there are a lot of words that don't make sense, but after a while, things really just start clicking. Nobody can immediately understand this stuff, but if you have the opportunities that I've had, I really think, just like learning a foreign language, most people can manage. Um, just like learning a foreign language, sometimes a lot of people don't want to manage, or you go learn something else instead. But um, again, I want to argue today that everything is more accessible than it ever has been. Okay, so let me back up and tell you a little bit about where I came from. I was born in Bearville, Wisconsin, one of the few remaining circus towns. And like many Midwest towns, we had to drive your tractor to school day. We made the national news twice in the last decade, once for banning chants of USA and once for a prom photo where dozens of boys were doing a Nazi salute. Our SAT and ACT scores and standardized test scores were the worst in the state, and back then that meant that the school would get less taxpayer money from the government as a result. But I did have passionate and qualified teachers, and our high school, although it didn't have AP physics, we used a textbook that was written by a cartoonist and a boxer named Paul G. Hewitt. And this textbook had no equations, no vectors, and almost no numbers in the entire book. And so when I went to the University of Chicago, where fun goes to die, incidentally, is the motto, it was a very intimidating time in my life. It turns out they barely use numbers either. The only, let's say, differential equations classes or linear algebra classes were proof-based, which means they do not help you solve physics problems. I did learn a lot of Greek, though. As an aside, my professors also completely missed certain subjects because they assumed other professors were teaching those subjects. So I majored in physics and computer science, and I did web programming job for a summer. And then the next summer, I had this weird idea that now I needed to try a physics job, but I didn't really have a reason why. So I heard about a professor who was starting a new atomic physics lab, and I went into his office for an interview. And I think he could tell I didn't really know what I was doing or where I was going. And he asked, "Well, you're going to go to grad school, right?" And I was going to tell him the honest answer, which is I really don't think about the future. I'm here today, uh, and I haven't planned, the next week, let alone the next 2 years. But I didn't. I said, I could tell he wanted me to say yes. So I said yes. And I considered that kind of a promise to him at the time. I worked with him for 2 years, and then I wound up here at CU Boulder in down the hall from Dwayne. The building's called Jella. So now I've been here for 6 years, and I've had a really nice time. And I wanted to leave a few observations. Number one, you've got an incredible opportunity here at CU Boulder. You may not know this, but the atomic physics program is #1 in the world. Okay, it narrowly edges out Harvard, MIT, who work together, and um, and the other programs are almost just as good too. The engineering department is fantastic, and the optics and the condensed matter, the high energy physics. It's all really good here. Undergraduates have a tremendous opportunity to join labs, and there's so many of them to join too. I realize that the pandemic has really thrown a wrench in a lot of people's plans, but um, you should just kind of be aware that there really are a lot of opportunities here. They can be a little intimidating to get into, though. And speaking of intimidation, I've always been surprised since getting to grad school that there really are no scary smart people here, possibly anywhere. So what do I mean by that? I always had this picture that there would be, oh, I don't know, 1 in 100 people here or something, but someone who could just skip all the classes or had already published many papers, built his own experiment or whatever. Um, and sure, there are people with more experience and people who work harder, but what I realized is everyone's really using kind of the same set of tools. Okay, so I talked about my limited opportunities in high school. A lot of my friends in college, they went to Dubai International School or Albuquerque Polytechnic School, where they were doing calculus at a college level in 6th grade. But it takes a lot of people to teach a whole subject, like quantum mechanics, for example, and it takes a lot of time too and investment. So everyone kind of reached the same point in grad school as far as the knowledge that they had, and we really felt like we were all at the same kind of level. Um, that was always a surprise to me. And number three, I wanted to make the point that it's probably never too late to change who you are and allow yourself to change. I've changed a tremendous amount since the beginning of grad school, and I feel a lot better about who I am as a result. On a personal level, my hobbies include hiking, woodworking, playing music, tennis, board games, singing sea shanties, eating cheese fondue. I've had a good time outside of physics here. Oh, I guess that's observation number four. You may sign up for a physics program, but there's much more to life than that. And so I wanted to break out here into some small groups, as I think you usually do in these CU Prime discussions, and mostly do introductions. And as a little bit of an icebreaker, it's kind of a personal question, but I pose the question: do you feel like you could ever belong in a physics or academia environment? Do you feel like you already fit in? Do you feel like you could belong in higher education, or like your professors are way smarter than you could ever be? And do you feel like it's too late for you to succeed? Um, these are a lot of the feelings I had, especially coming into the grad program, still have right now. So I hope Ian can help us break out into these groups and say hi to everybody. You're going to see these people later. Um, One thing that came up in our group was, well, maybe I should say, on a personal level, for me, I would never be comfortable in the past speaking about my vulnerability with a group of strangers, but I always had friends near me that we could find a way to uh, cope with our maybe insecurities or our struggles or our hard homework or whatever. And so whether that was ignoring the class by going out for a hike or we would um, uh, find some other way to deal with the kids in our class that seemed like they knew what was going on. Um, yeah, does anyone else want to chime in? Something that I realized, way too late in my physics career was I've always been terrified to ask a question and look like I don't know an answer, and I would just, I never went to office hours. I would never ask a question in front of other people, um, and that worked okay for me, I think, because when I figured it out, it made me realize, well, if I'm not going to ask somebody who knows, then I need to figure out the answer for myself. So sometimes it's just important to recognize these traits in yourself and then deal with them one way or another. Okay, so this isn't really supposed to be a big motivational talk, but I do think it's important to mention things like imposter syndrome, and that virtually every grad student feels it to some degree, or realize these other things about ourselves. And this question of what does a scientist look like, and the preconceptions that make it more difficult uh, for everybody. I'm going to share screen again here. I thought I was, but should be back now. Um, these preconceptions can be extremely damaging to people and also to fields, to the field as a whole. Okay, so I think we're ready to move on. Let me just check the the chat. Okay. And let's move on completely. This is a sudden, abrupt transition. So wake up. We're done with all that personal stuff. We're going to talk about science again, and I'm not even going to try to connect the first half to the second half. So to tell you about my work exploring quantum mechanics, we need to discuss a few ideas first. The first is superposition, which seems weird initially, but it's actually not that special. An example is rolling motion. And to understand rolling motion, we can consider it as a sum or a superposition of rotation motion. And I thought this was, did this just stop playing? Okay, so we can consider rolling motion, and then we add in translation and put them together. Oh, here it goes. There we go. And together it becomes rolling. As another example, consider waves. If we understand the motion of one wave, well, then the motion of two waves looks chaotic and complicated, but it's really just two things on top of each other. And we do the same thing for other types of problems in physics. For example, electrons in understanding circuits. And let's try a couple more examples, because there's a very common one in quantum mechanics that we consider. It's called the two-state or the two-level problem. And in quantum mechanics, it's very common to consider this coin that has two outcomes, heads and tails. And something has happened to initially put this into a superposition of heads and tails, something like a coin flip. So pretend this coin is spinning in zero gravity, spinning forever until, click, somebody stops it with their hand and they measure it, they have a look, and then the system collapses into one of heads or tails, in this case, heads. Okay, and the same thing happens in Schrodinger's famous thought experiment. This is purely a thought experiment, Schrodinger's cat. The cat is both alive and dead inside of a box. And when somebody opens this box, the cat has to choose a state, while the universe chooses a state. In this case, the cat lives. Now, that sounds very fantastical, but what really makes quantum mechanics interesting and unique is entanglement, which makes use of superposition, but it requires two or more objects. Okay, so consider this setup. There's two coins, a gold coin and a silver coin, and they start out in this system that I've made where the coins are in a superposition of heads, tails, and tails, heads. Okay, so Lucy is going to take the gold coin to the left room, and Ricardo is going to take the silver coin to the right room, and they're going to separate. Okay, Lucy to the left, Ricardo to the right. They've each got their coin, and these coins have been tied together in this way by me before they separated. Okay, so Lucy makes a flip with her coin, her gold coin, and she looks at it. She might get heads or she might get tails. Let's say she gets tails. And this is interesting. Before Ricardo even looks, Lucy can yell down the hall and tell him he's going to see heads. Well, how does she know? If we look back at the initial system, if Lucy gets tails, Ricardo's getting heads. Now, if she had seen heads, Ricardo's going to get tails. There was never a possibility for heads, heads, or tails, tails. And this is something that made Einstein very uncomfortable. These coins are correlated, they're tied together in a mathematical way. And nowadays, the normal way to interpret what happened is Lucy's result of the coin flip was random, and the unused outcome, in this case, gold heads, it just didn't happen. It's kind of gone forever. But by the way, the idea of the multiverse, if you've heard of that, says both outcomes happened, and now there are two branches of universes heading off, and I've got two different outcomes. We just don't have a way to travel between those universes or communicate or anything. Okay, if that wasn't surprising, let me put it in a different way. This might be the most important slide in the talk, and so I hope you'll follow this. There's a quantum cake factory shown in the picture here, and it's right in the middle of these two conveyor belts heading left and heading right. And every so often, this cake factory makes two cakes that come out at the same time in the opposite directions. And there's two things that Lucy and Ricardo, the cake factory employees, are looking at. Okay, number one, they want good cakes. So the cake at the end is either good or bad. But in order to figure out how to make good cakes, sometimes they open the oven halfway and they try to figure out if the cake is rising early or rising late. Okay, it's like a souffle. And sometimes it rises when it's supposed to, but when you open the oven door, no matter what, it falls down. It's ruined. You can't open a souffle. You can't open the oven door for a souffle halfway. It's a bad idea. Okay, if you take nothing else out of this talk, remember that. So either the cake rises early or it doesn't. But if they check, that cake is ruined. And either the cake tastes good or it doesn't. But if you taste it, you can't have checked if it rose early or not. Okay. So the cake factory employees, they find something very surprising. Number one, both cakes rise early 9% of the time together. Okay, so on Monday, they come into work and they just spend all day ruining the cakes. They open the doors halfway, both of them, for every cake, and they get back together and say, "Did your cake rise early? Mine did. Mine didn't." Well, 9% of the time, they both rose early together. Day two, one of them gets to spend all day eating cake, and the other one has to check the oven on the other side. So whenever Ricardo's cake rises early, Lucy's cake tastes good. Whenever Lucy's cake rises early, Ricardo's cake tastes good. Okay, and if you think about it, you may see where this is going. Okay, both cakes rise early together 9% of the time. When one cake rises early, the other one tastes good. So clearly, both cakes are going to taste good at least 9% of the time, maybe 100% of the time, but at least 9% of the time, right? But that's not right. This is a quantum cake factory, and something's gone horribly wrong, and both cakes never taste good together. Okay, and if I showed you this in a logic class, or if I showed you this 150 years ago, you'd say you messed up. That doesn't make sense. When I told this to my parents a week ago as practice, uh, my dad looked confused for 15 minutes. This should be extremely surprising. Okay, both cakes just never taste good together, and um, and and that's just a mathematical fact of how the universe behaves. Okay, there are underlying things um, going on that make sense to write down in math, but they don't follow in the traditional logical sense, in the classical sense. Okay, so we're going to get back into the breakout rooms and discuss broadly what you think of these ideas. Specifically, how are you feeling about these ideas that I've shown you? The superposition idea that a thing can be in two states at once, alive and dead at the same time. Is that crazy, or is that just normal? And then entanglement. Uh, have I got something wrong? Did I screw up? Does it seem too basic? Um, are you upset by the idea, like Albert Einstein? Maybe you can't understand me. Talk with your groups and we'll see what you say. Um, if that's not an interesting question, Ian pointed out that this one might be too tricky, but every time quantum entanglement comes up on a news story on the internet, people in the comments, they say, oh, okay, well, faster than light travel is just down the road. Won't be long. But quantum entanglement doesn't allow for faster than light communication, and I wonder if anyone can explain why not. So as an example, when Lucy and Ricardo take their coins to opposite rooms, it seems like she should be able to do something to her coin and send information right down to Ricardo. But it turns out she can't. It's okay if this is, I haven't told you all the information you need. So we'll just see what you come up with. So let's go back into the breakout rooms and have a little chat. Thanks. Hello again. So I'm very curious about this um, first question about what are you exposed to, especially coming out of high school or in your early physics classes, and um, do you have this preconception that entanglement and the math and quantum mechanics is going to be way too hard and nobody understands it, and or are the tides changing because entanglement makes the news more and more often, or at least a certain part of the news more and more often, and maybe uh, maybe more and more people are coming to terms with these crazy ideas. Does anyone want to share kind of what their group came to?
Yeah, Hassan.
Well, I don't really. We just kind of like our group. We just immediately started talking about like the multiverse theory and things like that.
Great.
And we started discussing like first I said that like wouldn't it like does the multiverse isn't that theory like flawed, because if a multiverse did exist, it would just be a universe still. Like it wouldn't really like I would just see it as just kind of like an extension of the universe. But yeah, we had our like different ideas. And then like like Morgan towards the end, like I think she kind of like answered the like bonus question. Like can I talk about it?
Yeah, please.
Okay. All right. So yeah, we got to like a point where we started discussing like things following a causal line of events, and we like determined that that's probably the difference between universes is the fact that one universe has its own causal line of events, like its own timeline, and then the second, like universe 2 would have its own timeline. And then we said that, she said that things couldn't move, like it wouldn't make sense for things to move faster than light, because then essentially the effect would precede the cause, which wouldn't make sense, because like cause and effect is sort of like predicated on speed of light. So
I think there's definitely something to that question, and and there's there's a ton of rich physics there. I won't go into too much. I was trying to figure out before this talk why. Okay, let me back up a little bit. The collapse in entanglement, it does happen, as far as we can tell, instantaneous. It happens definitely faster than the speed of light. That was shown, I think, in 2015 by about 3 groups all at once. People have been trying to show that for 20 or 30 years, and all at once, 3 groups were able to show that, yes, this linking up of results happens faster than the speed of light. So they separated particles a kilometer apart. They did both the coin flips. They took the coins, they got back together and said, well, there's no way that our particles could have been connected by photons and gone and shared that information. And so it has to be instantaneous. So I wondered, why does it have to be instant? Why can't it be faster than the speed of light, but slower than instantaneous? And it turns out that there's actually mathematical reasons in quantum field theory that I'll never understand. There's a reason for that. And you have the capacity to figure that out if you have time. But I wanted to, I didn't pose the question very well, so I wanted to back up a little bit and say, what do I mean by faster than light communication? There's this picture that people have that you'll take 2 entangled particles, we'll keep one on Earth and we'll send one out in a spaceship, and then when something happens, we'll send information, hopefully faster than the speed of light. And so what you'd like to do is you'd like to take that Earth particle, and when a war breaks out or something, or let's say you're visited by aliens or something, you take that coin and you flip it onto heads, and then the other people are looking at their coin and they say, oh, our coin just flipped to tails. Well, that just doesn't work very well. It doesn't work at all, because it's not allowed by quantum mechanics. The problem is that in order for this entanglement thing to work, you need that randomness of the initial coin flip. And this is not to say that the answer you were talking about is wrong. It's just a tangential point. There's still this randomness in making that initial measurement, which is a lot of what I wanted to talk about for the rest of the talk. So, when I was giving this talk to my dad, he said I'd put a window on the oven and then look at whether it's rising or not. And the funny thing is, that's just absolutely not allowed in quantum mechanics. It turns out that's exactly the same as opening the oven. Anything that's a measurement that tells you whether the cake is rising or not is going to cause the cake to fall down. And uh, so a type of measurement that is allowed is, yeah, that's exactly right. You know, photons are moving in and out of the oven, whether you have a window or whether you open the door. Um, and that was a comment in the chat, by the way. The type of measurement that is allowed, you know, you could put the oven on a scale and figure out, is there even batter? Is there even a cake in there? Because the cake weighs the same whether it's risen or not risen. And oh, sorry, there are several points here in the chat. I'll leave that to Ian to cover. So these are the kinds of things we think about. What kinds of measurements are allowed and are going to cause the cake to collapse? Sorry, are not going to cause the cake to collapse. And what type of measurements aren't allowed and will cause the cake to collapse? Right. As soon as you're aware of observing the cake has risen or not, as soon as anything in the universe could become aware, you know, it's liable to collapse. So, shall we move on, Ian? It looks good. I need to share screen again, don't I?
Yeah, you're all good.
Okay. I think we're back in presentation mode. I didn't get to show my cool follow-up slide, so let's just pause there. Okay. All right. Back to the quantum cakes. The thing I didn't tell you about this cake factory is the underlying state that it started with. And so kind of in the notation that we were using before, by the way, this is extremely close to the notation that we quantum mechanics use every day. We draw pictures, but usually instead of, you know, we're not very good artists, so we just start using letters like LG for left cake good. The cakes coming out of the cake factory, well, they were bad plus bad good plus good bad. And if you remember, we never had an opportunity for both cakes to be good at the same time. That just wasn't coming out of the factory. Okay. I haven't told you anything about rising or not rising. That's a little more difficult, and it's covered well in this paper that I stole this whole example from. I hope Ian can post the link in the chat. You now all have the ability to understand this paper, and I hope some of you will enjoy it. Okay, so for the rest of the talk, I want to get into what I kind of work on. We're in the midst of what some people are calling the second quantum revolution. The first quantum revolution was kind of the discovery or formulation of quantum mechanics 120 years ago, and they wrote down these rules for entanglement. But it's only been about 10 years that we've really become pretty good at creating entanglement. And well, what do you do with it if you can't send messages faster than the speed of light? What good is it? Well, there is a whole thing called quantum communication, but it mostly has to do with using entanglement to create eavesdropper-free communication systems, which certain people are extremely interested in. Maybe more accessible or more easy to understand is the appeal of quantum computers, which are poised to solve problems that would take supercomputers until the end of the universe. An example of the problem is called the traveling salesman problem. You've got, let's say, 20 cities on a map, and you've got a distance between each city, and the salesman wants to travel between each one by minimizing the total amount of gas that he uses in his car. And it turns out that if you compute, let's say, the total distance for every combination for 20 cities, well, you can do it on your computer, but it might take you a year. For 20 cities on your computer, it might take a year. And on a supercomputer, if it tries to compute 22 cities, it might take a year. That's how fast it grows. You know, the world's fastest supercomputer can't do more than 22 cities. Okay, and so by the time you're at like 24 cities, that supercomputer is going to take to the end of the universe just to figure out all of the combinations of distances. But a quantum computer could, in principle, solve that instantly. I can't prove it or show it to you, and we're still many years off from having that be a realization. What I work on is enhancing precision measurements by using entanglement. And what do I mean by precision measurements? I mean the world's finest measurements of electric and magnetic fields, of time and frequency and forces and accelerations and gravity. These are precision measurements that have all kinds of applications in magnetoencephalography, GPS, navigating nuclear submarines, and they have all kinds of applications for fundamental science too, including searches for exotic physics. Okay, and so I'm just going to breeze through these and say there's all kinds of plans to find dark matter and plans to collect all of these Nobel Prizes. All of these things are accessible with the kind of precision measurements that I'm talking about right now. So how do you run a precision measurement? Well, your job is to set up a system where the quantity of interest, maybe magnetic field, maybe time, it sets a probability for measuring heads and tails. So for example, 0.9 nanoseconds might set probability of heads at 0.4. 1 nanosecond corresponds to 0.5. 1.1 nanoseconds corresponds to 0.6. And in order to measure, let's say, a time or a magnetic field, well, you flip as many coins as you can and you determine how balanced those coins are. So you need to measure P. The problem is, if you've ever flipped a coin, well, you get one or the other. That's not a lot of information. If you've ever flipped 50 coins, if you've ever flipped 500,000 coins, you don't get exactly 250,000 heads. I ran the simulation this morning and I got 249,500. Okay, and I didn't repeat it. What you need to do if you want to do a good measurement is you repeat it many times. And if you repeat it 1,000 times, you get this distribution, which has this standard deviation. It's a Gaussian form and it's got a standard deviation that goes like the square root of the number of coins you flipped. And the point is, when you're flipping those coins, you'll always have these fluctuations to worry about. And so you can never do your measurement infinitely well. So again, you use 500,000 coins or 500,000 atoms so that you have all of these parallel sensors. But at a certain point, you can't use more atoms. They start bumping into each other and creating problems. You can't use better atoms for maybe an atom that's more sensitive to magnetic field. Well, at some point, you've chosen the best atom. And so the only way to do better is to use entanglement. So how does that work? In terms of coins, you measure the first atom, you measure that first coin, and you get heads. And like we talked about before, the outcome of that coin is tied to the next one. The outcome of that atom is tied to the next one after you've entangled them. And so by flipping one coin, you could know the next one's going to be tails. But now we've got 500,000 coins, which, by the way, is what we do in our experiment. And so they go back and forth, and they're all tied together. And we can know, basically just by measuring one, the fraction in heads. We don't know which ones are in heads. That's important. But we can learn the probability that those coins would be in heads. And we can do that without those fluctuations that we have from actually flipping every single coin. There's a picture for understanding this called the block sphere. I won't jump into it, but essentially that precision measurement is operating by a blob, a noise blob that spins around on the equator of a sphere. And if you pretend you have a clock here, then this looks like a clock hand, but it's a blurry clock hand when you have unentangled atoms. You should measure 530, but on a given measurement, you might measure 545. And you never know, did I get unlucky? Is it actually 6 o'clock and I got unlucky the wrong way? The only way to do better is to make your clock hand finer, squeeze down that noise in the clock hand direction, and you use entanglement for that. Okay, if you've heard of the Heisenberg uncertainty principle, where position and momentum are tied together, then you know that if you measure one really well, you hurt the other one, and so you end up stretching out this direction, but we don't care. In this case, the clock hand is on the equator, so we don't care about all this extra noise. Okay, in our experiment, we're almost done, by the way. In our experiment, we create more entanglement than anyone else in the world in any kind of system. We use 500,000 atoms and we squeeze that noise down by about a factor of 100, which looks like this. When we open our big metal door to the lab, it changes something. It changes the magnetic field, and we can easily resolve that the door is open or closed. But if we didn't entangle, we would have no idea. If you pick an individual point, I just don't know if that's going to be a red one or a blue one. So I don't know if the door is open or closed. I lied a little bit. We did get beat out for the entanglement record by a lab at Stanford that was doing basically the same experiment. But for most of my professor's experiment's life, he's had the record for the most amount of entanglement in any system. Okay, how do we create the entanglement? Really don't have time to get into that. It's quite complicated, but we use something called cavity quantum electrodynamics, which is a very fancy way of saying we have a cavity, which is a fancy way of saying we have two mirrors that point at each other. Just like, if you've ever entered like a hotel bathroom that has mirrors everywhere and you look in and you see infinite reflections back and forth. We put atoms inside of two mirrors that look like that. And those atoms float there. They're trapped by lasers. Okay, and then we shine a laser in through the back of a mirror. It bounces around about 150,000 times. Each photon bounces around many times before eventually it leaks through the mirror, and it carries off information about the atoms. So by bouncing it so many times, it interacts very strongly with the light. If you send a laser at a single atom, there's a good chance that atom doesn't care. But if you send it at that atom 150,000 times, it cares more. And so that's how we link all of the atoms together. We put 500,000 atoms inside of this cavity. We shine the lasers. We collect the information that's contained in the light, and we learn something about the atoms. Oh, sorry. One more thing. Cavity refers to the mirrors. Quantum refers to something with quanta, which are atoms. Electro refers to electromagnetic waves, which is light. And lasers. Dynamics means what happens. So all of this just means what happens when you put atoms and light together inside of mirrors. Finally, a day in the life of a physicist. Well, when I was putting this together, quickly realized it doesn't make much sense to answer the question. Every day is so different. Sure, we arrive in the morning and we say hi to everybody, we check our email, but after that, all bets are off. One thing that's very common is we run around the lab and we make sure everything looks normal. Nothing's broken. Nobody's changed anything. And we spend, a while each day fixing everything that's not normal. So this is a picture of our lab. We've actually got two separate experiments set up here. Each one's about the size of a very large dinner table, and then there's a second table behind it. So these are really labs experiments that 3 or 4 people work on. And here's a 3D rendering of what our experiment looks like. Very simplified. We're missing a lot of lasers and things. So inside of here is the cavity. You can't see it at all, but these things are creating magnetic fields. These laser beams are trapping those atoms inside of the cavity. And we send light up and it bounces back down, and then we learn about those atoms. Okay, so once a week, typically, we end up setting up new systems, new electronics, new optics, new software. We end up buying stuff. We end up doing some calculations. But it's always so different. I can't put a exact description to it. And once a month, we end up fixing something big. Something dies, a laser dies, and we have to completely replace it. We need to make a new metal part custom. We need to learn some new skill, which is something I really like about this job. Constantly learning new things. And about once a month, something good happens, and we get pretty excited about the progress that we're making. In this case, we were putting the experiment together. And so the cavity is way up here on stilts so that we can get these atoms far away from the big metal table, which has all kinds of magnetic fields. And we want these atoms as far away from the environment as we can get them. We put them in a big glass shield and we pump it down to vacuum. And we really try to study just the atoms and just the light together. Okay, and then about once a year, we do something like write a paper, go to a conference. I got to go to Barcelona last year. And we see our family and we re-explain all the work that we've explained to them many times. And in this picture, we were actually moving the entire lab from the second story down into the basement, which was not a fun thing to do. Fortunately, we do that about once every 10 years, I think. Okay. And so I feel like it's my obligation to introduce a quick advertisement. You have a civic responsibility to engage with your community, at least at a minimal level, which for most of us should involve voting. And I don't have time to prove that to you, but you're adults now. So go figure out how to register and then vote in every election for the rest of your life. And in exchange, I'm offering you 6 free tips for being a better physics student. Okay, so I'm going to run down these real quick, and then we'll reach the question period. Number 1 is there's a website called Archive that a lot of people are unfamiliar with. It doesn't make a lot of sense. It doesn't make sense to me. There's these journals that we publish to. We send them the paper. We pay them a lot of money, about $2,000. They look at the paper and they say, okay, this is good enough. We'll print it and we'll sell it to other people. You won't get any money back. Okay, that doesn't sound good to a scientist. They want their work read. So they do that for the glory, but then they also share the paper with everybody else for free on a website called archive.org. Totally illegal, nothing wrong with it. It's just this weird agreement that the physicists have because of tradition. So you can use the archive to find almost all the research papers that have ever been written in physics. Other fields, biology, they don't do this. You can maybe look at some patents or something. So I thought when I was writing this that I was going to link an archive paper, but I guess I didn't. So number 2 are review papers. The papers in the archive, they tend to be terribly technical and incomprehensible, even to the people that, when that Stanford group published their paper beating our entanglement record, I had to read that paper 3 or 4 times before it made sense, even though it's the same experiment I do. And fortunately, some people do try to write papers that everybody can read. And one example are review papers, which they may take a subject like spin squeezing or entanglement and try to make it so everyone can read it. So I hope Ian would link this Google search. It's literally a Google search for review paper spin squeezing, just to show you that a couple will come up. Not all of them, unfortunately. You have to search pretty well. And you might be able to read some of these. If you want to learn about entanglement, search review paper entanglement. If you want to learn about diode lasers, search diode lasers review paper. Okay. Number 3, the harmonic oscillator. 2 points here. When someone's teaching you something and you've seen it before and you can't understand why they're teaching it to you again, that's not an opportunity to skip it. And it took me about 5 times through the harmonic oscillator before I realized I never learned it once. You're going to hear this term over and over again. It's like the single best example in all of physics. It comes up over and over again. It's how everything works. If it's not a 2-level system, it's a harmonic oscillator. The light inside of our cavity is a harmonic oscillator. Okay, so I hope that word sticks with you and you pay attention because I never did, and I'm passing along that wisdom. Number 4 is do it yourself. One of our professors here said, okay, you can listen to 1,000 piano sonatas and enjoy them and pay very close attention, but it's not going to make you a better pianist. So you have to practice on your own. A couple times in my life, I've been extremely reliant on other people to do physics homework. Cutting those people at least out of the homework circle, my homework circle, and doing it for myself really helped a lot. Okay. You can still be friends with them. It's fine. And you should still, collect all the wisdom you can, intelligence you can from them. But at some point, you need to do it yourself. Number 5, cartoons, which is ironic because I complained earlier about this conceptual physics book. It turns out drawing cartoons is extremely important for communicating with other people, for simplifying problems to yourself, and for breaking down complex problems. You got to learn how to draw good cartoons. And 6 is learn to program. Maybe it's a given at this point. It's just going to take you to places that you couldn't get to otherwise. So with that, I thank you. I apologize if I've gone a little bit over time, and I thank my lab and the CU Prime hosts in particular. And I wouldn't be here if it weren't for you.
Awesome. Thank you so much. I'm going to do the awkward clap thing. Thank you for giving a fantastic talk. Okay, yeah, so are there any questions for Graham? I saw some questions in the chat. So
yeah, I'm really happy there was dialogue in the chat.
Yeah, so the first question I saw a while ago, or okay, Lachlan has his hand raised already. Would you like to, yeah, go ahead.
Okay, so my question is about quantum computers. I've heard that they're a bit niche for classical problems and that they can only really solve special cases, and that their real use is going to be in simulating quantum systems. What do you have to say about that?
I think there's a lot of wisdom in that idea. I think you're right. I've heard that too. There's a thing called universal quantum computers that it's kind of the analogy of having a full, desktop computer where you could program it and do whatever you want with it. And those are somewhere between 5 years off if you talk to somebody at a company like Google, 10 years off if you talk to a young scientist who's working and giving talks in a university. And I've actually heard from atomic physicists who work on trying to build quantum computers that they basically, I've heard this from two, and they both happen to be quite old. And they said, I really think it will never happen, which is a funny thing to say in physics, especially if you're working on the problem. You reach the end of your career and you're like, well, that's never going to happen. So a universal quantum computer would be immensely useful. I wouldn't say it's niche, but I would say there is a huge issue that there aren't enough quantum programmers. There aren't enough people writing smart algorithms. Okay. I have a friend in the engineering world in the wind energy part, and he's been trying to get me to take a postdoc trying to write algorithms for quantum computers. And I don't know why the wind energy people want someone to write algorithms, but I told him, I have no idea where to begin writing an algorithm for a quantum computer. Okay, that might be a good place for some of you to start. There's going to be many career options for these people. You don't even have to be successful. I was told by him, you don't have to write a single successful algorithm in the next 2 years. We'll give you the job. And you just have to tell us, like, what do you think is possible in the future? I said, I'm not even comfortable doing that. But yeah, okay. So the current quantum computers for companies like D-Wave, they do tend to solve really niche problems. And there's all kinds of debate about, are they even, can you even call it quantum computing? Is it a quantum simulator? And so on. And then there are definite algorithms that will revolutionize the world, like Shor's factoring algorithm. When it can successfully run on large numbers, it's going to break banking as we know. It's going to break the internet as we know it. Now, how do you solve the traveling salesman problem? As far as I know, nobody's figured that out yet. So I think the real problem with quantum computers is there's a strong suspicion among the mathematicians that, yes, they will solve all the problems, all the NP hard problems, but nobody knows how to write those algorithms yet. Other people may chime in or just tell me you disagree.
I saw Evan, you have a question?
Yeah, so last year, I remember there was a lot of buzz in the news about something known as quantum supremacy. And my understanding of that is that, and I could be horribly off base here, but it's that a quantum computer was able to do a calculation faster than a standard computer. What do you know about that?
Yeah, that's basically right. And it's a little bit like this traveling salesman problem, where you say, I would like to calculate all of the outcomes for 20 cities. And, it may take one computer a year, but it may take a quantum computer a very short amount of time. But it's like it's either you can build a good enough quantum computer or you can't. And for a long time, people couldn't build good enough quantum computers. Let me rephrase a little bit. Basically, practically what it means is a bunch of mathematicians said, I can simulate these coins that I've been talking about. I can simulate 2 coins just fine. That's no problem. I can simulate 4 coins. I can almost do that in my head. But I think the number was around 50, like 54. They said no computer in the world can simulate 54 qubits. So if you do a calculation with 54, coins, then you've done something new and interesting. And so Google and another company, I think Honeywell is right at that threshold, of 54 qubits. Now, the calculation they did is completely useless, but they got most people to agree, I think, that that they hit the number. They hit the 54 number and said, we showed we did something.
Shannon?
Yeah, not to sort of make this like a quantum computing like Q&A, but do you know anything about like the current state of like quantum computing and like where it's like where they're at and actually like building quantum computers? Like what's
Sure. So I know a bit. I mean, mostly through talks and general hearsay and stuff. There's some speculation that the government or U.S. government already has a quantum computer and they're using it to spy on everybody and break the internet. That's not true. Be interesting, but it's just not true. There are companies like Honeywell and Google that have really, and IBM, that have really appealing systems that are based in electronics, cooled down to almost, to superconducting temperatures, and they use these kind of artificial atoms to simulate. And the good news is they can get about 50 of them, printed on a board with silicon and stuff, and so that's great for getting about 50. But when you have the problem of, you want 500 or something, it becomes extremely hard. Then there are other companies that say, well, we'll take a different approach. We'll use atoms. We can pack 500 and we can pack 500,000 in. That's no problem. But now our difficulty is operating on each one independently. We try to shine a laser at one without hitting the laser on the next atom, and that becomes really hard. So there are trade-offs between the different technologies. Doing the operations on enough coins. There's maybe a third circle to this Venn diagram. You're only going to hear more and more about breakthroughs, and I think it's going to be another Moore's law. Moore's law, acceleration of technology doubles every 5 years or something. That's what I would say the state is. There is a really good report from the U.S. government on the current state. I think they do this every year. The U.S. government's building, and other national governments are building giant quantum information centers, both for the math portion and for the experiment portion. It's the new place to look for new physics now that the Higgs boson's found, and 30 years of particle physics kind of dried up. It's just too expensive to build bigger and bigger collider loops. So you can spend $10 billion building a giant loop underground, and your project may even get canceled before it even starts, like they did in Texas. Or you can spend $10 million building one of these tabletop experiments and probably find more physics.
Thank you.
We'll take maybe one more question, and then I think Graham has agreed to stick around for another 10 or 15 minutes or so to answer any other questions. So Hassan, what's your question?
Yeah, so I remember it's not related to quantum computers, but I remember towards the beginning of your talk, you mentioned that, you kind of alluded to the idea that you didn't really have any sort of formal mathematical training for a good portion of your academic journey. Is that true? And would you say that it's kind of did it negatively affect your position in physics, or would you say it was like a big handicap? Or
sometimes it was a good thing, because, for example, I think I was better at drawing these cartoons than other people were just so unfamiliar. We take first year physics classes where you need to draw these force diagrams, and there's no problem. It's like you obviously have the forces; they have to balance. It's whatever, and other kids just wouldn't get it, and they'd say, "Well, I got to write on the math." And I've learned a lot of math through programming and my programming classes, and trying to understand, differential equations when they're trying to teach it to us in Greek. And then the next day I'm taking a computer science class and they say, well, do a simulation where you have time steps. It's just like a differential equation. Okay, so so sometimes you pick up the math in a way you don't expect. That was, I think, one experience that I routinely had. Now, I did, I think, read certain books that helped a lot. Kind of popular science books in high school, and I had good professors in college, especially in terms of math. So I don't want to say I had a terrible math education, but I do think it was substandard compared to most people. Did it hold me back? I don't know, because like I said, I think it caused me to, if I was struggling, I would find some way to deal with it. I would find a friend who seemed to understand the math really well. Yeah, it's a good question.
Thank you.
Yeah, if anyone else wants to chime in about that, or stick around and we'll talk more. But thanks everybody for listening. And as I understand it, you're free to go without hurting my feelings.
Yeah, thanks for hanging around. Let's thank Graham one more time if you're going to leave. Graham, thank you so much for a fantastic talk.